Hello, everyone, and thank you for joining us this evening for the third week of the Rugby Research and Injury Prevention Group 2025 Analytics Series. Our first intern is Nadira Peaks from Adelphi University. Nadira will be presenting on confidence intervals. Nadira, may you please share your screen?
Thank you, Rivik. Yeah, I've requested to turn on my screen. Thank you. Can everyone see my screen okay? Thank you. All right, good evening, everyone. My name is Nadira Peaks, and today I will be presenting Understanding Confidence Intervals. Please give me 1 second. Okay, sorry about that. So, what is a confidence interval? A confidence interval is a range of computed values that estimate an unknown population parameter with a stated level of confidence. Confidence intervals only use variables from a sample, and they're a very useful tool in the field of inferential statistics. Population mean, median, and proportion are all examples of population parameters. Parameters describe data from an entire population. The level of confidence is the probability that a range of values for a confidence interval will contain the true value of a population parameter. So confidence levels can be expressed as percentages, being 95% or 98% or even more than that. So there are many different ways to calculate confidence intervals depending on what you are trying to find. I have included an example of finding the confidence interval of a population mean. So this is the equation for the population mean of a confidence interval. X bar is the sample mean, Z is the confidence level, S is the standard deviation, and N is the sample. The margin of error represents the amount of sampling error in a study, and it can be substituted for this part of the confidence interval equation. So when should you use confidence intervals? You can use confidence intervals when you want to estimate a population parameter, compare a sample mean to the range of population parameters, support data-driven decisions, or communicate statistical results clearly. A key thing to remember is that confidence intervals are the most useful when you have a sample data, but do not know the exact population value. So there are many applications of confidence intervals, and they are used when there's uncertainty about a population. For example, polling and surveying, you can use confidence intervals to forecast the outcome of an election or report public opinion. In the context of business and economics, you can predict sales or profits with uncertainty or inform investment and pricing decisions. In the context of healthcare and medicine, you can determine the range of treatment effects for a new medicine or improve healthcare decision-making. When interpreting confidence intervals, it is important to look at the width. The width of a confidence interval depends on the sample size and the variability in the data. A large sample size and a low variability of data means a narrow interval. And narrow confidence intervals indicate higher precision and greater certainty about the estimate. The following is a case study done using confidence intervals. So a doctor believes a new drug may help lower patients' blood pressure. To investigate this, he recruits 20 patients to take the drug for 1 month. Afterward, he records how much each patient's blood pressure decreased and calculates the average reduction. Based on the sample, the mean decrease in blood pressure is 80 millimeters of mercury, with a margin of error of 3.92, using a 95% confidence level. In the picture over here, we know that the sample mean is 80, the margin of error is 3.92, and the confidence level is 95%. When you plug that into the equation of confidence intervals, you see that the upper limit is 83.92 and the lower limit is 76.8. So the doctor will then say, with 95% confidence, the population mean for the true mean decrease in blood pressure is between 76.8 and 83.92 millimeters of mercury. So some important key takeaways are a confidence interval is a range of computed values that estimate an unknown population parameter with a stated level of confidence. Confidence intervals are the most useful when you have sample data but do not know the exact population value. And confidence intervals offer several advantages for different types of studies. They are especially valuable when estimating a population parameter. I've included some resources that will help from the internet, and I have included my references. Thank you. Are there any questions?
Thank you for the excellent presentation, Nadira.
If,
Yes, Dr. Lopez.
yeah, if you can go back, Nadira, to the sample that you brought up. Obviously,
Yes.
thank you for bringing in a clinical example. I think everyone's seeing this. This is the type of question you'll see on the MCAT. You'll probably see on step 1 of your confidence intervals. Now, what they'll ask most likely, and is I think the best example is between hydrogen ion and pH, this the acidity. There's a correlation here between confidence intervals and the narrowing, as you said, Nadira.
Yes.
The more narrow, obviously 76 to 83 is pretty narrow, right? So what is that going to possibly give us? It's going to give us the p-value that everyone always hangs their hat on, right?
Yes.
Some statisticians and some epidemiologists just use confidence intervals. They don't use p-values, so therefore they won't use a chi-square or something to calculate a p-value to. They'll just use the confidence intervals in their analyses and in their manuscripts. And we've seen this prior to this year with Maya, but before that, when we were really doing some heavy duty analytics, I think that's when we started noticing that different authors were using just the confidence intervals. So I guess maybe I'll ask you, Nadira, since you're presenting, right? The narrower the interval, the smaller the
P-value.
p-value, and therefore the potential for there being a significance of the outcome. All right,
Yes,
everyone? That's what they
significance.
always use when you use the p-value. They find out if it's significant findings or not. So you can just leave confidence intervals with a very narrow margin, and you know that that has significance.
Right.
Okay, everyone? All right. Now, there is a limitation with confidence intervals, and I just have to bring this up. So it's hard to, how can I say? There are some disadvantages, and what happens is it may not have or contain the population parameter you're interested in with confidence intervals. So you have to be very, very, how do you address that? Obviously, then you can make sure you do the p-value, you make sure that you've looked at the data of a particular population. So say hypothetically, let's break this down just for rugby, right? Right, we have forwards and backs. Maybe we could say, forwards that are offensively playing, right? So like a basketball player, right? They're coming across the key with the ball, they're being offensive. So a basketball player in an offensive position and therefore you have a very small, or your parameter of your population is very narrow. You know that that's an exact cohort. You're sampling from a particular cohort of finding that you want. So if you do have a narrow then confidence interval, therefore you know it's significant. If you guys understand what I'm saying, right?
Yes.
Everyone on the board. Anyone doesn't have a question, we ask now, so this way we can try to understand this, okay? So say you're also then you're a decathlon, right? But you only look at the long jump, that data. Therefore, you know you're looking specifically, you're not just looking at the decathlon overall, you're looking at that particular jumping mechanism and its influence right there, and it's prone to injury or not. You get what I mean? You're eliminating other alternatives, and therefore you get a population parameter that you're interested in finding. Okay.
Yes.
All right. All right, y'all. All right. Go ahead, please. Thank you for that one, Nadira. I think.
If I could actually also raise a
Yeah.
point, if Nadir, if you could go to the equation used for the confidence intervals, I think that this was a great touch in your presentation because it's important to understand that because the sample size, the n, is part of the denominator there, that really explains why it's important to have larger sample sizes and how sample sizes affect your confidence intervals. So as your sample size gets larger, your multiplier becomes smaller, and that leads to smaller confidence intervals and more precise values.
Yeah. So in theory, great point, Philip. All right. So we have forwards, or we have women and men, or then we have all forwards, or you get what I mean, or all players, and that makes our n larger, dividing it into giving you a more exact population parameter. All right, everyone. All right, great job. Let's go.
Thank you, everyone.
Thank you for the great presentation, Nadira. Our next intern will be myself, Rithvik Paniganti from Georgia Tech. I will be presenting on hypothesis testing and p-value. All right, so my presentation today will be on hypothesis testing and p-value. So what is hypothesis testing? It's a method to evaluate whether there's enough evidence to support a specific claim. So in hypothesis testing, you set up two hypotheses. First is a null hypothesis, which is basically no effect or no difference. And you have the alternative hypothesis, which means there is an effect or a difference. And the goal of hypothesis testing is to use data to decide whether or not to reject the null hypothesis. So an example null hypothesis is a drug has no effect. An example alternative hypothesis is that the drug improves lung function. So there's 5 steps to hypothesis testing. So first, state the null hypothesis and the alternative hypothesis. And second, choose a significance level, which is denoted by the alpha value. Most commonly, you will see an alpha value of 0.05. And third, run the experiment. Fourth, compute the p-value. And lastly, you want to compare the p-value to the alpha value. If the p-value is equal to or less than the alpha value, you will reject the null hypothesis. And if it's greater than the alpha value, you will fail to reject the null hypothesis. So what is a p-value? A p-value is a statistical measure that helps assess the strength of evidence against a null hypothesis in a hypothesis test. So basically, in simpler terms, it tells you how probable it is to get the observed data if there is actually no effect or relationship. So a small p-value, if you have a small p-value, then your null hypothesis is rejected. And if you have a larger p-value, your null hypothesis is not rejected. So let's visualize the p-value. So the curve, as you can see on the left, shows the distribution if the null hypothesis is true. So the red lines here are the critical values, which is the alpha value threshold. And the shaded orange regions is the p-value areas. So these are technically the extreme results. And as you can see in the image, it's the p-value region. If test statistic falls in the shaded region, then you'll reject the null hypothesis. So here, let's proceed with a real world example. So first, let's start off with a scenario. Imagine you want to test whether drinking caffeine helps students focus better during a task. So half the group will drink coffee and the other half will drink decaf. Everyone will complete a focus task and you will compare their average scores. So first step, like we said earlier, was set the hypotheses. So our null hypothesis is caffeine makes no difference. And our alternative hypothesis is that caffeine improves focus. And step 2 will collect data and analyze. And what you find is that the coffee group performed better on the focus test. And step 3, once you calculate the p-value, what it tells you is how likely is this result if caffeine really has no effect. And 4, you'll compare it to the alpha value. And here, let's say is 0.05. The p-value is low, for example, like 0.02. We say this result is statistically significant because it is less than the alpha value. So here you reject the null hypothesis and say caffeine likely helps. And just be careful to interpret it. So for example, if the p-value is high, like let's say 0.11, then you wouldn't reject the null hypothesis. But an important point to note is that that doesn't mean that caffeine does nothing. It just means that this particular study didn't show strong enough evidence to say otherwise. So a quick summary. Hypothesis testing helps evaluate claims using data. Once again, the null hypothesis has no effect. It denotes no effect, and the alternative hypothesis is saying there is an effect. The p-value tells us how surprising our result is under the null hypothesis. We'll compare the p-value to the alpha value, whether to decide to reject the null hypothesis. And once again, a non-significant result doesn't mean no effect. It just means not enough evidence. These are my references, and highlighted in yellow are the 2 videos that were attached with the Analytics Club schedule. Does anyone have any questions, or Dr. Lopez, do you have anything to add?
Sorry about that. Anyone have any questions?
I do.
Please go, Violet. Go.
You said that you compared the p-value to the alpha value. Can I ask what the alpha value represents and what does it mean in the data?
Yeah, I can show you right here. So as you can see in this image here, the alpha value is like the critical value threshold, as you can see with these red lines. So that's what we use when we're trying to it's a value that we use to compare the p-value to determine if something is significant or not. So it's basically like a measure comparison. So if we increase or decrease the alpha value, then that would change like how hard it is for us to determine if something's significant or not, like how much margin there is.
Thank you.
And just to jump in quickly, if I do remember, a p-value of 0.05, I believe correlates to a 95% confidence that the data will support the H1 hypothesis. And anything, they also have different markers for p-values as well, 0.01, and it gets smaller from there for other basically levels of confidence.
And just to add another thing, I think there was a presentation last week on type 1 and type 2 errors. So if you recall that, the alpha value is a type 1 error, which is basically your accepted possibility of a false positive. And so that's just determined by whoever's making the calculation, just to bring that back to the type 1 and type 2 errors we learned last week.
So when do we, I guess, thank you, Dr. Dawson. So when do we apply this 0.01 or more, I guess, a stronger evidence of real effect, right? This will probably be less so in our injury analyses, but more so maybe in drug testing. right? Where we need to have a stronger level, a stricter threshold, if that's the best way of phrasing it, right? And when you do these tests on these drugs, please just continue without me if I get.
Okay. Our third intern is Minna Ko from Lighting Academy. Minna will be presenting on describing distributions, shape, center, and spread. Minna, may you please share your screen?
Can you see my screen? Um, sorry, I just need one moment. Okay. So, hi, today I'm going to talk about how to describe data distribution. So we're going to look at three big ideas, which is shape, center, and spread. And these datas can help us to tell us how to like look at data and how they show up all the time on the SAT math section specifically. So I guess like a really big idea is like why does it matter? When you describe a data set, you're basically going to summarize what's going on. On the SAT, you're going to be asked how to interpret graphs and compare graphs or understand the certain average of or like what the range means. And knowing how to break down the shape, center, and spread of a distribution will help you to answer those questions. So we can start with the measures of a center. So that's where most of the data tends to cluster. So there's three main ways to describe them. There's mean, which is the average of all values. There's a median, which is the middle value when the numbers are ordered. And mode is where the value shows up the most. Each one can tell you something slightly different. For example, the mean is sensitive to either really high or really low numbers, while the median can give you a better sense of the typical values if they're outliers. So next is spread, which is going to tell you how much the data can vary. So here's the key measures. There's range, which is the gap between the highest and the lowest number. There's the interquartile range or IQR. That's the middle 50% of the data between Q1 and Q3. And then there's also standard deviation, which is how far each value is from the mean or the average. So knowing the spread can help you to see how consistent the data is. The small spread would mean that data points are close together, while larger spread means that there's more variability. So I'm going to talk about the shapes of distribution that can give you an overall picture of how the data is arranged. When it's symmetrical, the left or right side should look about the same. If it's skewed right or has a positive skew, there's usually a longer tail on the right, and usually the mean is greater than the median. If it's a skewed left or there's a negative skew, a longer tail on the right or on the left, sorry, and the mean is less than the median. If it's uniform, all the values occur roughly at the same frequency. And if it's bimodal, that means there's two peaks showing two clusters of data. And being able to recognize the shapes can help you decide which measures makes the most sense and what kind of patterns might be present. So a real world example could be, say we're looking at test scores in a class. If most students scored around an 80 with just a few higher, a few lower scores, the distribution is probably symmetrical. But if a couple students scored really high, those scores could pull the average up and create a right skew. By checking the shape, center, and spread, we are able to get a much fuller picture of how the class overall performed. On the SAT, you might see a graph and be asked which distribution has more spread or whether a set of data is skewed. There are all different ways of whether you can understand the center, spread, or shape. And once you've got these concepts understood, then you'll be able to better tackle these problems quickly and accurately. So just like a recap, the center is usually talking about the mean, media, and the mode can all help us to find the typical value. The spread would be talking about the range, the interquartile range, and standard deviation, and these all show how much the data varies. And the shape can tell us how the data is distributed and if there are any trends or outliers. And together, all these tools can help us to understand and communicate what a data set is really showing. Thank you.
Thank you for the excellent presentation, Minna. Are there any questions, or Dr. Lopez, do you have anything to add?
I'd like to actually add something. I think that it was really great that you mentioned how if it's skewed right, you can think of it as the tail being on the right, but also that the mean would be greater than the median because it can be a bit um, difficult to understand because it's a bit of like an inverse relationship where if it's skewed right, of course the tail will be on the right, but the hump of the curve will be further left. So that is a bit confusing sometimes. So I think it's also great to not just think about it as the tail being on the right when it's skewed right, but also the mean being bigger than the median, because of course there's the higher values that are increasing the mean.
Yes. So go ahead, Nadir, please.
And hey, your presentation was great. I had to ask, when you have a bell-shaped curve or a normal shaped curve distribution, where is the mean and the median?
Usually the median is like quite like in the middle still, and the mean it depends on, or it's still like I think it's still usually in the middle because once you get the average, it should all be like pretty even.
Thank you.
So we often use in epidemiology the median, right? We want to know what's the point within the population that is most important to distinguish your skew to the left and skew to the right. We're often looking at that because when we're looking at large data sets, we want to find out where our point is to distinguish. And again, it moves, but I believe it's best to think of it when we try to find out the median as the significance of the data. And that's probably the best way of saying it because the significance of the data we're looking for, we say, oh, what's the median of that knee injuries? And then when you're looking at burden tables, you're looking at the median finding of the outcomes. So it's to look at where you are with injuries. And that's probably what we look at the most within our data sets. Now that we're dabbling into the nutrition, things of that nature, or other data sets, the responses and the response rates will probably also be influential. So just to clarify again, it depends on the data set you're looking at, and the data set will then dictate what kind of analyses you want to do and where your median and mean are, but also how I think Nadir, you alluded to your bell curve, where it lies. Because if you look at particular data, it may not be as that simple bell curve where, hey, and I think Larry and Lucy know this the most when you're trying to pass these exams in medical school, that's you're just looking at that bell curve the entire time to find out where do you fall in the animal kingdom, where do you fall, and do you pass, did you pass well or did you pass high, or thank God I think my school was just pass or fail. Lucy, yours too?
Just for the first, well, no, we had like honors for the first 2 years, or we had like a high pass, and then they added the honors for the clinical rotation. So
Like I
it's
said, it
supposed to be,
varies what
yeah.
university, boys and girls, you're at. but at this stage in the more professional realm, they just want you to know that, you're passing and you're passing, within, you're passing with the wolf pack up in the front, or you're not. And you need to know for that for yourself, because then you go, okay, I'm going to have to study better for that, for the, step one. And that's strong. It gives you a good reflective measure of where you want to be. And I like I said, it depends on the data that they're looking at. I'm just giving you the example in regards to grades on exams, which is probably what most of you will be looking at when you're looking at SATs, Minna, and obviously with Larry and Lucy in regards to any of that. Larry, is your school pass or fail, right? You pass or fail, right?
No, we get grades.
Really? Wow. All right. Interesting. Gotta set the standards. I'm just, it's important. I guess the varying institutions do that. That's why I asked. I did not know. So again, also, kids, the more important thing is that I believe, Larry, how old is your school?
I think 2013 was the first class, or 2017 was the first graduating year.
2017. So it's a newer school. All right, guys. So it probably needs to set the standard. Therefore, when you have those grade numbers, and I think you all know that are an undergraduate, you're vying with each other from organic lab to biochem, you just, and I don't mean to bring it up, Lucy and Larry, to traumatize you if you remember those days, but you're pushing amongst your peers to advance your grade, and you need to get the best grade possible. So the importance of that is, you're still in that realm where you're trying to get the best grade possible, right? They seem to associate the correlation that, if you do the best you can academically, numbers wise, that you're going to be the best student. I don't know. I think now that when we come out on the other side, we look at everyone in a roundabout way. And I think Dr. Dawson and Dr. Kangro will agree with me. It is. I think you probably see people with very different, diverse backgrounds, educations, degrees. And again, I don't know if you guys all know, I'm just going from the medical school perspective that, and even if you talk, let's talk about something even different, the veterinary school perspective, right? I think 20% or 30% are non-science degrees. They're getting music, archaeology, art and literature, something different degrees, but they're still taking their cores, their science course. It's just very different, very unique. In regards when you start looking at that, I don't know if I can actually say that there's a particular formula that they're looking for yet. But I do tell you that I can tell you from a surgical or a procedure-based resume what they're looking for. I can tell you, so I can definitely knowledgeably tell you what they're looking for regarding that. But I can't tell you getting into medical school or why different residencies choose interns in their pool of population. I do think this is very unique. Like I said, that whole match thing is very, very different compared to when I did it. And like I said, it just changes the dynamics of things. And that's why, we're fortunate to have these upper peers when you want to ask them these questions, because like I said, and I think that's why I presented that the other day. I brought up some of the slides of how many hours. And again, I try to use as most recent data possible, so you understand when I'm giving these, I'm looking at it from what they're looking for now. What are they looking at? And trust me, I know what they're looking for, at HSS. I can't tell you what they're looking at other institutions for. Dr. Ma and I actually had this conversation the other day. and we were talking about it because they want to do something. But again, how do they look at it? Well, first of all, you definitely have to be on the higher level of the bell curve. Fair enough, right? You all have to be at the higher level of academia, your grades, your exams, and then you put all those together, and then they look at other things on that aspect as well. But don't mean to take that in that direction. But thank you, Minna. That was a very interesting presentation because, again, I'm glad you used the review books for the questions. Everyone else, you should all be using the MCAT questions, and they have YouTubes and all that. So you should be incorporating this because that's what we used to do in the subject matter. When when you're presenting with your service, whatever it is, use the question from step 1 from that service. It'll be, significant for everyone there and be significant for you, or step 2, now that you, Lucy, and then step 1 for Larry. You should be looking at those questions and put them in your presentations in a scenario the way, you guys did. And I like that, Nadira and, Ritvik and then Minna. By bringing in those questions, you bring in like the samples of how they're going to ask the question on the exams. We used to do that. We used to take the questions from the previous year's exams and just try to, jam them in somehow. You try to absorb the data the best way you can, everyone. On that note, thank you, Minna. Any questions more for Minna on the bell curve? Excellent. All right, everyone.
All right. Thank you, Minna, for that excellent presentation. That will conclude our call for today. We thank everyone who joined us for the Rugby Research and Injury Prevention Group Analytics Series. Once again, thank you to everyone in the audience as well. Yeah.
Excellent. Thank you so much, everyone.